All right, does anyone have any questions about the upcoming exam that I haven't written yet and it's going to get written today? Yeah,
I'm a little nervous about not getting homework 2 back before the exam.
yeah, I'm not planning to cover too much of what's on homework 2 before on the exam. How much of homework 2 was on the study guide that I didn't quite cross-reference?
I think a lot of it.
Was a lot of it? I will try to make it very homework 1 heavy. And then curve as needed if things become. If the exam scores are as bad as the homework 1 scores, there will be some curving.
Okay. Thank you.
The exam is Friday. Right?
Yeah, exam is Friday in class on paper, note card allowed.
Just front sided.
Front and back. And then anything incredibly algorithmic, I don't want people to memorize, so I will try to include any algorithm on the exam, but it will probably be in its most technical form. So being able to read the technical language that we have in class will serve you well to be able to understand what the process of the algorithm is that is given to you on the exam. Other questions? All right, last time we started covering the pumping lemma, I want to start back at the beginning of that, just because this is an especially difficult topic. And I want to give people the opportunity to kind of start fresh with that, with any understanding that you got last time and build on that as we cover this again. And then go through the last example and some more examples, because we need lots of examples of this. This is probably the hardest thing we've done so far. All right, so we said there's going to be some infinite regular language. We want to find some integer m such that any string in that language with length greater than or equal to m can be decomposed into subcomponents x, y, and z, where the length of x, y is less than or equal to m. This means that in order to get to the cycle and experience the first iteration of that cycle, those are all going to be new states. If we, in X, if we get back to a state that we had seen before, that's a cycle. So instead of being part of X, it would be part of Y. So getting to a cycle and then utilizing that cycle to get back to some state that we've already been in, every state that you visit along that path has to be a new state. So what that means, it has to be less than or equal to m, where m was the number of states. And also, so there exists some positive energy that we're going to link to the number of states. The length of y, the length of the cycle, has to be greater than or equal to 1. Such that we can now decompose and come up with a number of strings in the language by pumping this cycle. By repeating and iterating this cycle an arbitrary number of times, we keep coming up with more and more and more strings in the language. This is true for all regular languages. All infinite regular languages. So you can do this for any sufficiently long string in the language. You can break it down into those 3 parts, such that you have an arbitrary number of repetitions. The middle part results in another string in the language. So we're going to use this concept to show that a language is not regular by pumping that middle section, pumping the cycle, and showing that the resulting string is not regular. So find such a string where if we pump the middle segment, then it results in a string not in the language. So we introduced the pumping lemma game, which was played between 2 players. We have player 1, the antagonist, trying to make life as hard as possible for player 2. And if player 2 plays intelligently and the language is not regular, you can always defeat player 1. So player 1 picks the value for m, says that, all right, we're gonna come up with this value m, where you get the opportunity now as player 2 to find a string in the language greater than, with length greater than that m. right? Greater than or equal to that M. Usually there's a very intelligent way to do this, such that you pigeonhole player one into making a decision, a suboptimal decision. Back to player one, they choose, given your string, the decomposition X, Y, Z. Adhering to the constraints on the prior slide, the length of X, Y has to be less than or equal to the M that they chose in the first round. And the length of Y, this cycle, has to be greater than or equal to 1. And the goal of this is to make it as difficult as possible for player two with this selection. But with an intelligent selection of the string, player one will have nothing that they can do that will make this impossible for player two. And player two picks the number of repetitions such that the pump string X, Y to the I, Z is not in the language. If this is successful, player two wins and the string is not in the language and the language is not regular because of it. And then we mentioned this aside, just because player one wins the game does not mean the language is regular. So you do not want to go through this process to show that a language is regular. You want to go through this process to show that a language is not regular. This process is way too difficult, way more difficult than drawing a DFA or an NFA or producing a regular expression. So that's what you want to use to prove something is regular. So here was our first example. Show that a string followed by that same string in reverse is not regular by using the pumping lemma game. So player one picks M, whatever M happens to be. Usually this will not matter. If the language is not regular, the value of M does not matter. You will pick a string that has a value based on M. So we want a string such that the first M characters are all A's, and the string W is of the form A to the M, B to the M, which we already know is not regular. Right, because there were two constraints for player one. They now need to pick a substring of this, starting at the start of the string, such that the length of XY is less than M, which means that all of these characters that they pick for the part of this has to be A's. We have made a string such that they can only pick A's, which means that when we pump this, we're going to be producing more and more A's, such that there are more A's than B's. If there are more A's than B's, then when we reverse the string and use the old number of B's followed by the old number of A's in reverse, it does not adhere to this form. Does that make sense? I'll probably give you an example. Let's say M equals 3. In this case, we're saying we're going to pick a string of the form A to the M, B to the M for W. So what is the string that we are picking that represents something in the initial language? It is A, because we picked M as 3, so we're going to pick something with the form A to the M, B to the M. So we want 3 A's followed by 3 B's. And that is W. What follows is WR, that same string in reverse. So we're going to start reversing this, B, A. So if M is 3, we need to pick a string of length 3 or greater. Well, 12 does the trick. 12 is greater than or equal to 3. So we pick this string. Going back to player one now needs to pick something, needs to decompose. So the length of XY has to be less than or equal to 3. And the length of Y has to be greater than or equal to 1. So that means that X and Y have to come in the first 3 characters of this string. And somewhere out here is Z. All we know is the thing that is going to get pumped is somewhere in this sequence of A's. If we were to pump this sequence of A's, we should be able to come up with more and more and more strings in the language if this is regular. If we pump stuff in here, we end up adding A's. Is this string in the language? No. Is this string in the language? No. So we pigeonhole player one into making a decision of decomposing this first three characters into X and Y such that they can't win. So player one is now forced to pick an X and a Y that are all A's. And then we pick any I that is not one and come up with a string that's not in the language. So it doesn't matter for them if X is A and Y is AA, or if X is AA and Y is A. No matter what they pick here, when we pump this, we're just increasing the number of A's. Whether it's an additional 1 A per pump or an additional 2 A's per pump, it doesn't matter. It's easy to find an I. Any I is going to result in a string not in the language. How are we doing with that? Does that process make sense? Did the example make sense? Ish, kind of. So we have a string in this language. Player one picks some number M. Doesn't matter what it is. We're going to now construct a string based on their selection of M. Note that if they picked an M that was some different value, we would have picked a string that was of different value. If they picked M equals 5, we would have picked the string A, B, 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 A. But we have some kind of algorithmic way of selecting that in some way. The reason we picked this form A to the M, B to the M is we know that it's not regular. And if you pump something on the first half, you end up with something not in the language. So that was the intelligent selection of this particular form. This is the hardest part of this entire process, is figuring out the form of this first thing, such that when the player one goes and does this, they can't succeed. So if we had M equals 5, and we still use this form A to the M, B to the M, then player one now needs to adhere to these rules. The length of X, Y is now going to be less than or equal to 5, because it has to be less than or equal to M. And then that allows them to decompose this section however they want. If you're player one, what X and Y do you choose? It doesn't matter. It doesn't matter what they pick, they're going to lose no matter what they do. And that's because of what player two did here. So here they have more options. They could pick X and Y being the first character in the next 4 characters. They can put X as the first 2, Y is the next 3, X is 3, Y is 2, but it doesn't matter. Any selection they make is going to pump more A's at the start of the string, producing something that's not in the language. Are there any questions about that?
Does it all, so like, we're using the form A to the end, do we always have to use that form in the
No.
other units?
Player two gets to choose this form here.
Is it more often than not beneficial to use a form that's like that, or?
Not exactly like this. You'll have to use something where you think about the rest of the game. Think about what player one has to do here, and then pick a form where they can't win. Oftentimes, that is the hardest part of this, because it may not be immediately apparent or immediately obvious what the best choice for that is. That's an intuition that you have to develop by doing this a bunch of times. So step one is to understand the process, I think. I think at this point, if you understand this process, you're in a good place. So M is just a number. Doesn't matter what it is. Player two picks a string. This can be any string. Doesn't matter what the string is. It does. Some strings will help you prove this, and some strings will be completely pointless and not help you prove this. So intelligently selecting a string is the hard part, but you select a string. There are no limitations as to the form of this string, anything else about the string. Player one now picks the X and the Y. If this language is regular, infinitely regular, then you will be able to select an X and a Y that pumps this into more and more and more strings in the language. If it is not regular, there will be some string you can pick such that this is not possible. So identifying which string that is, or a string in a particular form, is really useful. Then player two gets to pick the number of repetitions, pumps, to find a string that's not in the language. I think at this point, it might be beneficial to move on and use some additional examples, and maybe with the additional examples, things will come together. Unless there are specific questions that I can address, if there are any specific confusions or not understanding a particular step, explanations of a particular step, I'd be happy to do that. Okay, so this was basically the same thing that I drew on the board. Basically, we have some number of A's, MAs, MBs, MBs, MAs. Regardless of what player one picks for M, that's going to be what this looks like. Then player one goes back and picks an X and a Y. We have set this up such that those are only going to be A's. Whatever value of X and Y they pick, we can pump the Y, which is just more A's. And it's no longer in the form WWR. Because this is W. This is WR, the same string in reverse. If you pump something in the first half, this second half is no longer going to be the reverse of that string. Which is why it's not in the language. In fact, the first half and the second half won't even be the same length anymore. The first half will be longer than the second half, which is obviously not in the language. Okay, let's do another example. All right, alphabet AB, language, strings with more B's than A's. Any string with more B's than A's. We want to use the pumping lemma game to show that this language is not regular. So player one picks M. The idea of all of this is that we want M to not matter. So we need to intelligently pick a string W that is in this language that is at least M characters long. So let's say they pick an M that is 4. And it's dying on me. What is a reasonable choice for W? You get to choose any string in the language that has more B's than A's. But it needs to be at least 4 characters long. Think for a bit about what kind of string would make this easy. Idea?
Like 5 A's and 6 B's.
5 A's and 6 B's? I think this will work. So if we do something like 5 A's and 6 B's, back to player one, what do they have to do? What was player one's task?
If the step to assign X, Y, Z
Yeah, they need to assign X and Y, which assigns Z by
default.
default. Such that, what were the constraints?
That X, Y, the length of that has to be less than or equal to M.
So M is 4, X, Y has to be decomposed in these first 4 A's. What is that going to do as soon as this gets pumped? Something in here, some Y is gonna be in this set of A's that gets pumped.
It's just explode default, like.
Yeah, we'll be able to choose some number of repetitions of this that produce more A's than B's. Is that string in this language of all strings that have more B's than A's? No, that's going to be our counterexample and our proof that this language is not regular. So in general, we pick this string for this M, but you can pick A to the M, B to the M plus 1. And if you do that, that will work in general for any value of M that they pick. We picked A to the M plus 1, B to the M plus 2 here. That will also work. Anything that guarantees that this XY has to be in the A's so that we start with only one more B than A and have to pump A's. That's the intelligent selection here. Note that this language has more possible strings where the A's and the B's are not together. If we were to give this as an example string, and XY has to be less than 4, they could pick the X as ABA and the Y as B. If they pick the Y as B, we now need to pick some number of repetitions of the B such that we produce a string that's not in the language. That's not possible. So remember that they get to pick how X and Y are chosen. And that makes a huge difference about whether or not it's possible to actually continue with the proof. So the string that you choose here is extremely important. You want to make it so that player one is pigeonholed into making, they can't make a good choice. Here, there's a good choice for them. Does that concept make sense? Any questions about that? So again, we have A to the M, B to the M plus 1, or really any A to the M plus K, B to the M plus K plus 1. Any of those will work. Why is this good? Y is restricted to be all A's, which is necessary because as we pump Y, the resulting string has to be in the language. Sorry, it can't be in the language. So the resulting string is certainly not in the language, which means that it is not regular. All right, one more example, because we need lots of examples for this. So we have another language, AB to the N, A to the K, such that N is greater than K, and K is greater than or equal to 0. So just like before, player one is going to choose M. So if we want to not win this, or sorry, if we want to guarantee that we're going to win this, we want to be able to pick a W that's based on M. So it's always best to come up with a string that's not just a particular string for a particular M, but for a string that is based on, has the variable M baked into it somewhere, such that regardless of what player one picks for M, you immediately have a string ready as the string you want to choose. So think about this for a few minutes. What here is a good choice for W? This one's a bit harder.
Person to pick an M button. Yeah.
So if you write W in terms of M, then it doesn't matter what they pick, you get the string that's based off of it. So yeah, if you want to start, we can say something like, sure, they pick an M equals 5. And see if you can come up with a string, but then try to generalize your result in terms of M, so that regardless of what player one picks as M, you have a string ready. Does anyone see anything? This one's particularly tough, so I don't necessarily expect people to see this. But I want to go over the answer and why the answer makes sense, because I think that will help you to be able to generate future answers to difficult questions. So here is a good choice. Before moving on, think about why this might be a good choice. What are the associated restrictions on X and Y, and how does that help us win the game? So in the case of M equals 5, we would have yeah. For some reason, I thought I counted 6. You're absolutely right. There should be 6 though. So in general, what has to be true here? What has to be true about x, y? Regardless of the value of m.
The length of x, y has to be less than or equal to n.
Yeah, which means that it comes from which portion of the string?
Beginning.
Yeah, something with repetitions of a and b. So now, the choice for y has to be split into cases. So we don't know what x and y are going to be. Player one gets to choose this. So now we have to think ahead about, okay, if player one chooses a y that is in this kind of form, what do we do? A y in this kind of form, what do we do? A y in this form, what do we do? So in this case, m equals 5. So these first 5 characters are all a part of xy, which means that y could be, you have a choice of what possibilities. What could y be? A, it could be BA, it could be AB. Technically, if M was 6, then it could technically be AB. It could be ABA, it could be BAB. So we need to be prepared to pump any of those things. By selecting this, we have to be ready to pump those things and show that they're not in the language. Or that there's something that's some number of pumps such that it's not in the language. So if y equals just a, we can choose I equals 0. And that removes a from the string, which means that we have 2 b's in a row. Any string that has 2 b's in a row cannot possibly be in that language. So check. If y equals AB, we again choose I equals 0. And this n is greater than k clause is broken because we chose AB to the m plus 1, a to the m. Now, if we chose an AB to the m plus 2, a to the m, this would not work. So this had to be AB to the m plus 1, a to the m, such that if we set I to 0, we remove one AB. And that sets n equal to k, which violates this language. And you can continue this line of thinking for any possible choice of y, and for the most part, you just set I to 0 most of the times and delete that subsection from the string, and that produces something that's not in the language. This was far and away not as easy to see as the last two. This was very difficult to see. You have to do a lot of forward thinking and a lot of planning at the step of choosing W, because your choice needs to work for any potential choice of Y that player one could make. So these arguments can get reasonably complicated. This game can get reasonably complicated, and you'll need to do a lot of thinking at this step to be able to choose something that works. We'll just quickly go through one more of these. For instance, why does BA, or how does BA not work? What could we do as player two? What value of Y can we pick if they pick a value BA? And again, this would only be possible if something like M was 6, and we extend it out here because Y needs to follow X. So it would need to be able to end in an AB. Sorry, not AB, that would be true for AB. But BA is perfectly fine at M equals 5. So if they pick BA, what do we do? I is 0. What happens if I is 0?
N equals K.
Yeah, it's the exact same thing as AP, then N equals K again, and we violate the language from N is greater than K. Precisely. And with any string longer than that, you will also be able to set I to 0, and for the same reason, N will be less than or equal to K. For anything that's longer than this. So you can show that by deleting some substring of this, you violate that principle. Giving a little bit of time for this to sink in because I know it's not easy, it's not straightforward. Coming up with a good W may not be intuitive yet. Question?
Just so I'm clear on so I'm not quite understanding like where it's from. And
Yeah.
I kind of get how it's used, but it's not clear. There's not a clear connection.
Okay, let's draw a quick DFA, a simple, not precise DFA. So we have our start state. Via some process, we're going to get to somewhere that's going to be able to, so this is the X part of our string that gets to a state that loops via some number of states back to itself. That's a Y. And then we get to some final state eventually, and this is going to be Z. We'll call this some QF. So again, we're doing basically this concept in a DFA. We know that in any regular language, any infinite regular language, there's going to be a cycle in the DFA. So basically, we're saying by this, we're kind of pseudo constructing a DFA, saying that is there a way to create X and Y within some value of M that gets you to a cycle and around a cycle within some number of characters that's being read. So we need to be able to come up with a string that's at least that long so that we could construct a DFA that would register that string with that many states.
So how much times you iterate through that loop?
Exactly.
Okay, we're good.
Yeah, so y so I, or y to the I, sorry. Y to the I is the number of times that we're going through that loop. So by setting I to 0 for each of these, we're basically saying, get to this point, don't do the cycle, and then go to a final state. And if we do this process, what we generate is a string that's not in this language, so we should not be in a final state. Which basically says that there is no DFA that could produce that string. Or sorry, if it produced the original string, there's no way that it could produce the pump string. If we could make a DFA to register this language, then if you delete an A from it, the DFA could not possibly register that language. If we deleted an AB from it, it would not register that language. If we deleted a BA from the string, it would not be able to register that language. And even if it did, it's not in the language, so you'd be reaching a final state without it being a string in the language, which says that no DFA can exist to pump this. It's a weird proof. It's a weird proof type, but it works. I will not go through the proof of why it works, because I don't think that's super necessary for you to know off the top of your head. But the process by which to prove something is not regular is useful in compiler construction. Other questions I can answer before we move on? There will be many more problems coming in homework that I can help you out with, that you'll get more practice with, opportunity to ask some questions before you're tested on it. So even if this isn't 100% certain yet, don't worry too much. I think the most important thing is to understand the process.
Are we gonna go over the homework one answers at all?
Come to office hours. All right, next thing we're gonna want to do is talk about some pitfalls. So what I see students do most when utilizing the pumping lemma And being aware that there are some no-nos that people try to frequently do. So the first one, we've already talked about a little bit, trying to use the pumping lemma to show a language is regular, you can't do it. Even if you could theoretically show that no string in a language can ever be pumped out, there are counterexamples to this of regular languages where this is not the case. So you cannot use it to show a language is regular. The next one is starting with a string that's not in the language. We specify the language at the start of the problem. And then if the W that you choose is not in that language, your proof is void at that point. So you need to start with a string in the language. So for instance, the language is a to the n such that n is a prime number. If you tried to say, given m, let W equals a to the m. Why can't we do that? Yeah. Yeah, exactly. Player one might have chosen an M that's not prime. So you cannot assume that player one chose an M that is prime. You could instead say something like, choose an given M, let W equal a to the next greatest prime number then M. You could use that. Some additional assumptions about the decomposition of X, Y, and Z. So we're going to use the same example, a to the n, such that n is a prime number. You could say something like, given M, let W equal a to the k, such that k is odd. Subtracting an odd number of a's from a prime number means that xz has an even number of a's and cannot be prime. What issues do we see? Where's the flaw in this logic? Yeah,
Set k to 3, subtract 1. 2 prime.
who is prime? That is a problem. But there's still an assumption that we're making that is not a legal assumption that we can make. That is a very good point, though. The answer is that we cannot assume that k is odd. We have to define W in terms of M, not K. M is really the only variable we're allowed to use here. Because this K may violate portions of the M. So you have to be somewhat careful about the arguments that you use and the assumptions that you make. Questions about any of these common pitfalls that I see in these kinds of problems? All right, that's everything I have to say about the pumping lemma. I don't think it's anybody's favorite topic in this course. But it is a necessary part of understanding languages and language composition, we very much need to be able to prove that a string, or sorry, a language is not in a particular class. And this is the best known way to do that. I will at least motivate the next section. Won't go too much into it because we don't have a ton of time, but we're completely done now with regular languages. We have seen everything that we need to see about them. So as far as we know now, they're a class that we can talk about. We can prove that something is regular, we can prove something is not regular, but now we need to start talking about the next class of language, which is the context-free language. So we can use the pumping lemma to show that a language is not regular. Why in the world are we going to care about languages that aren't regular? Think about some particular programming constructs that cannot be captured by a regular language. We have a string, A to the n, B to the n. Does this remind you of any particular kind of programming construct? What if we replaced all A's with a left curly brace and all B's with a right curly brace? We could start to make some interesting decisions about some nested structures. This wouldn't allow us to have successive nested structures, but it would allow us to maybe capture recursion or capture some other programming constructs that we've seen in other programming courses. So being able to show that something is not regular means that we need more than that finite amount of memory to be able to represent that kind of construct and be able to, if we're going to parse that kind of construct and determine whether or not a particular program is well formed or not, we need languages that aren't regular to be able to recognize those kinds of constructs. So that's where we're headed with context-free languages. We will start talking about that tomorrow.
I think it's last at the same time.